Okay, once again, welcome back. Before I introduce our speaker, I have a few requests to all of you has joined us. Uh, we appreciate if you can increase the attendance. So whoever is joining us continuously, you have seen we have great presentation in the past, and we will have more to coming. They are really, really exciting. So please spread the word and help us to increase the attendance so that we can disseminate these great seminar and their experience uh, to all of us in the agronomy. With that, so today's speaker is Ian Williams. He's an assistant professor in the Department of Geology and Atmospheric Science at ISU. His previous research, he was working at Lawrence Berkeley National Laboratory. His research focused on atmospheric and terrestrial ecosystem sciences, which includes land atmospheric interactions, water and carbon cycle, and climate feedbacks. Right now, his current research focuses on cloud resolving numerical models and observations to understand cloud scale rainfall process that are missing or poorly resolved in the global climate models. Today, specifically, his seminar will talk about on the role of surface water and energy fluxes in summer rainfall or the agricultural US Great Plains with a discussion on the usage and limitations of global climate, climate earth system model for future hydrological projections. Uh, so with that, I would handle the screen to the Dr. Ian Williams. Thank you.
Oh, thank you, Ram, for the introduction. And thank you to the Graduate Student Club for the invitation. So I will be talking about connecting the surface, boundary layer, and convective storms in Earth system models. These are essentially climate models that represent the role of vegetation in climate and the carbon cycle. The boundary layer is the layer of air above the surface that responds directly to changes in surface energy and water fluxes. So my research over the past several years has been focused on improving numerical prediction of the water cycle, specifically by advancing our understanding of the role of the land surface in cloud and precipitation processes. And the ultimate goal of this work is to simulate the impacts of energy and land use decisions on ecosystems and water resources. So I know Ram asked me to speak about solutions for Midwest agriculture. I don't know if I'll get to the solutions, but hopefully you'll have a little bit of a better understanding of the kinds of models that we are using and how we are trying to improve the representation of the Earth system in these models to make future projections. So here we are at the land surface. We know this is an important component of the Earth system. It's where water, energy, and momentum are exchanged with the atmosphere. Through those exchanges or fluxes, we know that the surface can feed back on and potentially amplify climate extremes. So intuitively, a wetter surface would put more water vapor into the atmosphere where it could potentially return as increased rainfall. We're also modifying the surface of the Earth, clearing forest for agriculture, as well as intensifying our use of the land surface for agriculture. This is showing, trends in the past 100 years of the rate of photosynthesis, where you can see these large changes in places like right here. So we'd like to know how these changes in the land surface will impact climate, how that might affect statistics of drought and floods in the future. Probably the most powerful tool that we have is numerical modeling in climate and Earth system models. Climate models were originally designed, of course, to simulate or to predict radiative effects of greenhouse gases on global average climate. So we have difficulty in predicting regional scales, especially climate extremes over land. This is one example of the summertime warm bias in the CMIP5 as a collection of climate models that were used in a past IPCC report. You can see a tendency of the models to drift toward these excessively warm and also dry states, particularly over areas that we're interested in for agricultural reasons. These biases can be a consequence of the lack of propagating convective storms. These are, by that I just mean thunderstorms that develop over the high plains and Rockies and propagate eastward over the central US. And it could also be a consequence of errors in the land surface, how it represents evaporation, as well as a combination of atmospheric and land model errors that could contribute to too strong of a feedback between the soil moisture and precipitation. And we know that the land surface is involved in these biases. You look at the first 10 days or so of a climate model simulation, you can see the drift toward a very dry state with rapid depletion of the model soil moisture in the first 10 days. And this is compared to forecasts that are reinitialized or essentially nudged back toward atmospheric observations. So this is a problem for predicting timing of if we're transitioning into a future drought-prone state, just simply because the model's own climatology or historical baseline is already about as dry as it can become. And those problems are carry over into trying to predict changes in the distribution of Earth's ecosystems. This is an example from the NCAR dynamic vegetation model where the composition of ecosystems is allowed to change. So grasses can replace forests. And what you see on the left is the uncoupled simulation where the vegetation model is forced with the observed climate. And it does a good job of predicting the distribution of, say, grasses. You see those over the central high plains, for example. But when the model is coupled to the climate model, it predicts grasses taking over eastern US forests and the Amazon forest, even in the historical climate where we know that the model should be predicting forests. And this is a consequence not only of errors in the atmospheric model precipitation, but also in how the model represents coupling between the land surface vegetation and rainfall. Specifically, the authors of this study point out that the strong coupling produces a complex hydrologic cycle where small changes in precipitation are accentuated by the changes in the model vegetation. So of course, clouds are a mediator of this sort of coupling between the surface and rainfall. Over most agricultural areas, the growing season rainfall is primarily from these kinds of convective clouds or thunderstorms. These are clouds that occur on scales much smaller than a climate model grid cell, which I've shown here in the red box. And so we call these sub-grid scale processes. And what that means is that we have to parameterize those effects of those clouds on the grid cell precipitation and climate based on the properties of the resolved, larger grid cell, typically using some kind of physically based hypothesis with a lot of empirical data going into it, as opposed to directly resolving the clouds themselves on a discretized space and time grid as we would with numerical simulation. And so that means that a lot of the subgrid scale processes are either missing or are maybe not accurately represented, and that can include things like the effects of land surface heterogeneity, which we know have an impact on clouds. You can see looking out of an aircraft window clouds on one side of the rabbit-proof fence in Southwest Australia, which separates the natural from agricultural land, as well as clouds outlining the rivers in the Amazon forest. So for the remainder of the talk, I'll talk about the role of vegetation, which maybe surprisingly has been sort of overlooked a bit in these studies. And then I'll talk about the impact of land-atmosphere coupling on climate prediction, how we can address some of the problems that we're seeing in climate models by thinking about the errors in how the models represent this coupling, and then the impacts on convective storms. And I'll divide that section into a first part on what we call single column climate models. These are computationally simpler, as well as satellite observations, and then finally turning to more computationally expensive cloud resolving models at much higher resolution. So as agronomists, this is probably a review. There are two broad pathways we talk about with regard to land-atmosphere coupling, which is a very broad term, and I'll be talking mostly about the stuff on the right side, which is what we call biophysics or biogeophysics, momentum, latent heat flux, and sensible heat flux being exchanged, as well as the effects of surface albedo. Biogeochemistry is typically a slower time scale, modifying chemical composition of the atmosphere. And just to make sure we're all on the same page, so what we call the latent heat flux is the surface energy lost due to evaporating water into the atmosphere. And the sensible heat flux is likewise the energy that typically is lost to the atmosphere from the surface that goes into raising the air temperature. And those two branches are actually connected, the chemistry and physics at the leaf surface. And as I'm sure most of you know, CO2 is taken up through the stomata in the plant leaves, which when they're open for taking up CO2, there's a necessary loss of water to the atmosphere in the form of transpiration, just because both are exchanged, water and CO2, through the same opening. So that's a necessary loss of water to transpiration, and living plants are designed to at least attempt to maintain an unbroken chain of water from the soil, from the root zone to the leaves to facilitate a hydraulic flow. And that's an important distinction with soil evaporation, where in the sense that as the soil begins to dry, the top layer, it begins to dry, the water becomes more tightly bound to the soil grains, opening up these air spaces, which can then disrupt the hydraulic flow, making soil evaporation more diffusion limited and a less efficient process than transpiration, as long as the root zone is sufficiently wet. So I'll return to this throughout the talk with regard to the role of plants in land-atmosphere coupling. So we measure this coupling in terms of, well, there's a lot of ways to measure it. One is what we call the evaporative fraction, which is just simply the ratio of the latent heat flux to the sum of sensible and latent heat flux. And we divide by that sum because the net radiation received at the surface is controlled largely by the atmosphere, and particularly cloud cover and the amount of solar radiation received. And so by dividing by the sum of latent and sensible heat flux, we're looking more at the control of soil and plants on evapotranspiration. And so I'm discussing here the chain of processes that connects soil moisture and vegetation to the evaporative fraction, which would then modify the properties of the boundary layer over the surface, which can influence the probability and amount of clouds and potentially the likelihood or amount of precipitation. So the evaporative fraction has a direct influence on precipitation amount. Just intuitively, you're putting more water into the atmosphere with a high evaporative fraction, which means more water for condensation and rainfall. But what's less intuitive is the potential indirect effect by changing what I refer to as the subgrid scale dynamics, these smaller scale processes. The turbulence in the boundary layer that's driven by having a higher sensible heat flux over a dry surface, which can at times be beneficial for triggering convection. I'll discuss that in some detail. So when I first started this work, there was actually quite a bit of uncertainty about just how important is land-atmosphere coupling. The reason was that earlier studies widely cited had identified areas where climate models had indicated substantial coupling of soil moisture to evapotranspiration and rainfall in these very regionally confined zones, including in the central US. But subsequently, observational studies had indicated that that model coupling was too strong. This is showing one example of the evaporative fraction with a lot of scatter in the relationship to soil moisture. This is daily timescale data. And one of the reasons, well, when we try to understand, well, why is there that scatter in the observations? We turn to a conceptual model, which is the prevailing view of how evaporative fraction is influenced by soil moisture, or how evapotranspiration is affected by changes in soil moisture. And what you see is that in very wet climates with high soil moisture, we expect that evaporation is mostly energy limited. So how much energy is supplied by the atmosphere for these fluxes? In dry conditions, the evaporation is just limited by not having enough soil moisture to sustain that flux. And it's these areas in between, which are referred to as transitional, where we expect a linear relationship based on a rather crude understanding of the role of the vegetation in facilitating that flux. So if we don't see this strong linear relationship, it could mean that climates are often atmospherically controlled. There's a net radiation energy is really limiting evaporation, or maybe it's too dry. But it could also mean that we've really grossly oversimplified how vegetation responds to soil moisture. And of course, that's a function of, as I showed, it's coupled to photosynthesis. And we know that that responds to light, temperature, and nutrients, and is not just a simple function of soil moisture. So are we looking at the wrong mechanism, or have we oversimplified this? So to address that, I looked at Ameriflux sites. These are surface flux measurement sites across a precipitation gradient across the US, including the Southern Great Plains site, which is a Department of Energy. It's the atmospheric radiation measurement site in the Southern Great Plains, or SGP. This is the SGP site. It's not a very wet site. It's also not an arid site. It's water limited in terms of vegetation growth. It's not, at least until recently, as far as I know, it's not widely irrigated. What you're looking at is actually two sites that I'll show. The one in the plot here in green is the winter wheat field, which has a distinct seasonality with the emergence of the winter wheat in the fall, and then reaching maturity in the spring. Whereas the grass field to the next to it is a mixture of C3 and C4 grasses. So you'll see a peak in the leaf area index there month or 2 months following the harvest of the winter wheat. So the first thing I did is to just reproduce results of our colleagues showing this weak relationship of the evaporative fraction to soil moisture. And you can see, this scatter that we saw in the figure I showed earlier. These are, again, daily daytime averages of the evaporative fraction over a period of about 10 years. And what I did is I replotted that data as a function of a measure of vegetation state, the leaf area index. This is inferred from radiometers on the ground on those two different fields, so the grass and the winter wheat. And you can see that evaporative fraction is much more tightly coupled to the vegetation state, or at least that's a better predictor. And you see the same thing for the winter wheat sites, a lot of scatter in the relationship to soil moisture. This is in the upper 10 centimeters compared to a much stronger relationship to leaf area index. So it indicates the role of vegetation as a mediator of this coupling, or it's a conduit of water from the soil to the atmosphere. That's not to say that soil is not important, but the effects of that are strongly dictated by the status of the vegetation. And what I like about these sorts of sites where you have very contrasting phenologies is you can really get at the causality of what's driving differences in the heat fluxes. So just by taking the difference in evaporative fraction between the two sites, the grass minus wheat, you can see that that difference is itself a strong function of the difference in leaf area index. And so this really unambiguously demonstrates the impact of vegetation on the surface fluxes, because the two sites have very similar climates, like nearly identical meteorology. So we're essentially conducting a kind of controlled field experiment. It works in dry climates as well. This is a grass site in southern Utah, Corral Pocket, which is a really fun place to be, by the way. So what I'm showing here is, again, the evaporative fraction as a function of soil moisture, color-coded by the day of the year. So most of the rainfall, or most of the precipitation, comes in the wintertime. So you're seeing this very clear pattern of the evaporative fraction going up in the spring as the vegetation leaks out or becomes active, and a decline in the summer months as water stress sets in. These are just 2 years, a wetter and a drier year, showing, you're starting off with a higher soil moisture in the wetter year. And, this is perhaps surprising to at least some of us in the atmospheric community, just how well the pattern of the evaporative fraction is mirrored by the CO2 uptake, or a measure of photosynthesis in a broad sense. It's net ecosystem exchange of CO2. So it's, again, illustrating this role of the vegetation as a controlling factor in the surface evaporation. It works also in a much wetter climate. So this is the Morgan-Monroe Forest in central Indiana, broadleaf deciduous forest. So you can see now the impact of the leaf out in springs. This is a period of something like 2 or 3 weeks. You see this abrupt increase in the evaporative fraction, and then a gradual decline as the soil moisture is depleted. Looking at a slightly drier site in central Missouri, you see, again, a similar pattern. And here, there's at least 2 years where we have evidence of drought stress. So there's a very nonlinear pattern in this relationship between evaporative fraction and soil moisture. So the approach of using correlations is probably not going to work very well, or at least linear correlations. And the reason for that is largely the vegetation processes that impart this nonlinearity. And you can show that by, again, recasting the problem in terms of a measure of photosynthesis, so gross primary productivity now on the x-axis. And so I'm showing this now linear relationship. And it's not very much changed even if you separate the data into the wetter and drier halves. So it shows that photosynthesis is still important in determining evaporative fraction, even in the drier half of the data. So to conclude this section of the presentation, this concept of the evaporative regime, controlled by either soil moisture or radiation, really needs to be expanded to think about the role of vegetation. If you do that and you use measures of vegetation state as your land surface variable instead of soil moisture, you will then infer a stronger coupling or more important land surface. And you find that regions of this measure of coupling extend well beyond those kind of narrow regions that were highlighted in the study that coined the phrase hotspots of coupling. So what impact does it have on climate prediction? Of course, I'm an atmospheric scientist, so I really am curious about, does this really matter for climate prediction if we are trying to improve or address biases in climate prediction? Can we do that by improving the way that the models represent land surface processes? And I address this question first in a computationally simple way. So using the grid cell of a climate model centered over the DOE site in the Southern Great Plains, first using an uncoupled land surface model, the community land model, CLM, with prescribed phenology and prescribed atmospheric forcing. So just the land model. And then I determined whether we can modify some of the parameters controlling evapotranspiration to try to better represent what we see in the observations at this site. And then to address the question of the impact on climate, I implemented those parameter changes in a single column version of the community Earth system model. So typically you'd run this model globally, but here I'm extracting one grid cell to make this computationally feasible, where we can test a lot of different parameters. So this figure you've seen before. This is the grass site in SGP. Evaporative fraction is a function of soil moisture and leaf area index. And below that is the simulation, the model run from the CLM, from the land model, with the default set out-of-the-box parameters. And what you see is that the behavior of the model coupling is pretty much opposite of what is observed in terms of the model predicts this tight coupling to the soil moisture, whereas the observations show that the evaporative fraction is more tightly controlled by the leaf area index. And to address that discrepancy, I increased the minimum stomodal conductance and increased the resistance to soil evaporation to try to make more of the evapotranspiration take place through transpiration, as well as improving the leaf area index data set based on what we measured on the ground. And that actually had a positive impact on the predicted evaporative fraction. So it tells us that we can better represent this relationship of evaporative fraction to leaf area index by modifying the parameters to shift some of the evapotranspiration more toward plants in the form of transpiration, leaving the net evapotranspiration largely unchanged, actually. And so here's the impact. This is the influence on the grid cell climate. You can see in red, this is the model predicted surface air temperature for 2006. This was a drought year in the Southern Great Plains. And you can see that the default model drifts into a much warmer state than was observed, whereas the modified land model parameters eliminated that warm bias. So again, it's indicating that later in the summer, there's less sensible heat flux because more energy is going into transpiration. And so that's reducing the surface air temperature. The modified parameter set also is able to capture almost all of the precipitation events, whereas in the default, precipitation largely shut off. So this is a single column where the impacts of the surface could be somewhat magnified by the lack of feedback to the larger neighboring grid cells. And so what we did next is took those same parameter changes and implemented those in the global climate model, CESM, with our collaborators at Lawrence Livermore National Lab. And what we found is that, in fact, those changes in the model parameters do have an impact, at least on the surface air temperature, less so on precipitation. But you can see that the summertime warm temperature bias is significantly reduced in the simulation with the modified land model parameters, so allowing more evapotranspiration to occur through the transpiration mechanism. So that's a promising avenue for maybe alleviating some of the issues that we have with some of these climate models. So the conclusion is that it's not that the coupling is too strong, it's that it's wrong. The models don't really have the right mechanisms to convey that coupling. And it has an impact on climate prediction, specifically the heat extremes and drought. So we think we can better represent the coupled processes to reduce some of those biases that we're seeing. So I'd like to now shift toward the smaller, what I call sub-grid scale, the cloud scale of rainfall. We call this convective initiation. This is basically just development of thunderstorms and their organization, from more or less individual cumulus clouds into clusters that then would become heavy rainfall producers. So I'll refer interchangeably to convective initiation and triggering. It's just, the mechanism that gives rise to buoyant cloudy airs. This is really a sequence of processes which is manifest in shallow cumulus clouds becoming deeper into deep enough to produce rainfall. So triggering is a precursor to most summer rainfall. It's a subgrid scale process. The climate models struggle to get these mechanisms correct. It's also potentially a negative soil moisture precipitation feedback, which is perhaps counterintuitive. So intuitively, you would think you make the surface wetter, either more densely vegetated and transpiring, or higher soil moisture, and that just puts more water in the atmosphere where it can return as rainfall. So positive feedback on soil moisture and vegetation. But a dry surface doesn't just do nothing. It produces higher sensible heating, and that increases the boundary layer, the near surface air temperature, making the air buoyant, where it can rise in thermals or waves in the boundary layer, which can then be mechanisms for initiating thunderstorms from that rising motion. And that's a negative feedback in the sense that rainfall could be more likely over a dry surface, over dry soil, in certain environments where the rainfall is limited by the initial trigger for getting these clouds to grow deeper. And the problem that I addressed first is just, how do you know which state you're in? If you're looking at a day in which you expect that a dry surface is more favorable than a wet surface for initiating convection. So that's the question. Are there environments where convection is limited by the trigger as opposed to the amount of water vapor? And the hypothesis, it can be illustrated in this schematic. So you have some variation in soil moisture on the x-axis. It could be temporal or spatial. It doesn't have to be heterogeneity necessarily. And that will impart a variation in the evaporative fraction, depending on whether vegetation wants to use that soil moisture. And that will affect the evaporative fraction. Now, we can imagine in a very dry atmosphere, it may be that no amount of surface evaporation is enough to condense water in clouds. But in that same atmosphere, maybe if the heating goes into sensible heating over a dry surface, that could increase the boundary layer depth. So you have more buoyant rising thermals, a deeper boundary layer where air can cool by ascending to a level where it reaches saturation because temperature decreases going up in lower pressure. So this is a mechanism for triggering convection over a dry surface. It would be tempered by entrainment of air into the boundary layer as it's growing. So it depends on the properties of the atmosphere above the boundary layer, as well as the depth of the boundary layer also depends on the properties, specifically the stratification, the thermal stratification above the boundary layer. So that's a factor. So we call this the negative feedback regime, which is an environment that we think would support convective clouds initiating preferentially over these dry surfaces. It's not really a new concept. It was discovered in simplified models. But since then, we've seen a lot of contradictory observational evidence or mixed support for this. And my idea was to revisit this mechanism with a more complex set of models. So starting with the single column climate model physics, which incorporates much more of the boundary layer turbulence and cloud processes than could be incorporated in the earlier studies, as well as more realistic input data so that we can actually hindcast past observed days, forecast what would have happened if the surface were wetter or drier, so that we can categorize observed days into these different regimes or environments. So using the single column model, again centered over the Southern Great Plains site, I categorized 15 summers into either negative or positive feedback, triggering feedback regimes by experimentally manipulating the soil moisture in the numerical model. Of course, we would like to do this in the real system and just go over a whole grid cell in a large area, make it wetter or drier. We don't have the ability to do that in a controlled way. So we use numerical modeling. I'll show that the results do depend on the choice of convective parameterization, which is not surprising. But I'll focus on the results from the UW or University of Washington shallow cumulus scheme, which incorporates more of the physics that we think is necessary for capturing these effects. And so we ran these simulations perturbing the soil moisture, looking at when did the model predict convective initiation over dry soil more often than over wet soil, and we call that the negative feedback regime. And to characterize that, we plot all the data on this two-dimensional phase space, like a state space describing the environment of the atmosphere with relative humidity on the y-axis and stratification on the x-axis. So the negative regime is where we expect deep energetic boundary layers. And so to just simplify the outcome of the simulations, I've just written on this slide that 27% of all of the simulated days fell into this negative regime and 23% were in the positive regime, meaning that in the negative regime, 20% of the time, if the surface were made sufficiently dry, the model would predict that the real atmosphere would have seen initiation of deep convection. So that tells us where to look, on what days to look for these connections of the surface state to convection. And what you can do, one of the things you can do is then compare the model prediction to observations. And since the critical variable is the boundary layer depth, we can look at days where the simulation predicted convective initiation in the negative feedback regime. And you see that, in fact, those are days where the model predicts a deeper boundary layer, a drier surface. And in fact, it's quite similar to the observed statistics for boundary layer depth. This is showing the increase in boundary layer height over the afternoon hours. Similarly, in the observations, we see a deeper boundary layer and a drier surface. As I mentioned, the results do depend on convective parameterization. So this indicates that the choice of parameterization has an impact and is potentially a candidate for explaining some of the warm and dry biases that we see in these models. You can also take those regime categories, definitions, and look at the satellite observations conditional on those regimes. So this is showing the diurnal cycle of cloud occurrence frequency as a function of height and time in the diurnal cycle. This is showing from 6 a.m. to 8 in the evening. You can see the transition from shallow cumulus to deep. And what we did is further divide the data into these feedback regimes. This is the negative regime. And then we took the difference between the wet and the dry days in the observations. And you can see this strong response of the convective initiation with shallow clouds growing deeper on the drier days in this regime. So that 58, there's an increase in the probability of a transition from shallow to deep convection of about 58% over these drier days compared to wetter days in this regime. And just to drive home the point about the state of the atmosphere as a controlling factor, if you don't separate the observations by regime, you find this very weak signal in the observations. So the state dependence is really important in trying to understand these feedbacks. So lastly, this is now looking at simulations at much higher resolution, so we can turn off convective parameterization. We don't have to worry about the assumptions that go into that, and we're actually resolving some of the larger cumulus clouds that are responsible for these thunderstorms. Again, we ran experimental hindcasts, or we manipulated soil moisture using as a guide to the case selection our earlier hypothesis of how the state dependence works out. So we selected cases that we think would show a negative versus positive response. This is just to show that a lot of work goes into developing the land surface input data sets for these high resolution simulations. So if you're interested in that, we just published a paper on trying to more accurately characterize this complex pattern of different phenologies of the winter wheat and grasses at this site. So putting that all together, this is an example of one case that really showed a clear negative triggering feedback. So we ran 2 experiments with a drier and wetter surface. And so I'll just advance forward in time to show through the afternoon hours. You can see that in the dry experiment, clouds developed over the study site that did not develop over the wet experiment. So these are cumulus clouds starting to organize into clusters. This is outgoing long wave radiation. So what you would see if you were looking at a satellite image for weather. And it confirms the empirical and single column model results that there are these environments that would favor development of thunderstorms over a drier surface. And lastly, more recently, we're looking at the whole feedback, so including the effects on precipitation amount. And this is a subset of the 18 simulations we ran where we're looking at these larger clusters of clouds that we call mesoscale convective systems. And what you see is that initially, and this is again local time in the afternoon, evening hours. So initially, there's no effect or even a negative effect of a wetter surface. This is wet. This is the rain rate difference between the wet and the dry experiment. So you see that the wetter experiments in the negative regime actually produce less rainfall, which is consistent with the negative feedback. But what's interesting is that at later stages in the cloud development, all of the simulations show a net benefit, for most of the simulations, show a benefit of the wetter surface in producing higher rain rate. So this is a positive feedback that develops in the later stages of the convective system. So to summarize this section, there is a feedback between soil moisture and deep convection, triggering of deep convection that depends on the state of the atmosphere. These are two different mechanisms for initiating convection that we need to represent in Earth system models and climate models. But once the convection is triggered, what we're seeing is that there's a positive sort of relationship where the wetter surface, in fact, leads to heavier precipitation. So I'll stop here with a summary of these sections. We're finding that models underestimate the role of vegetation. They don't accurately represent those effects, and that has an impact on drought and heat extremes, contributing to warm biases in the climate models. And maybe counterintuitively, that doesn't necessarily mean that the models are over predicting drought and heat extremes, because actually, because of the nonlinearity, you can't really get much drier in some of these models than their historical climate. So when you take the difference of the future and historical, you're not really maybe seeing as much of a change as we should be seeing. So this is a problem that we think we can address, as I've shown, by improving the representation of vegetation and its coupling to the atmosphere. So hopefully I've shown that the models are not a black box, and that a lot of the challenges can be addressed by thinking about the physical processes, specifically thresholds and nonlinearities in the system. So thank you for your attention. I will turn off my screen sharing.
Thank you, Dr. Williams. It was a great talk. We appreciated it. I can start asking some questions while the audience is thinking about their questions. So you mentioned that you use MODIS and leaf area index data. Were they daily data, or did you summarize them like for monthly to make them monthly, like, or weekly?
Yeah, so the data I used is approximately every 2 weeks. So it's probably just enough to capture most of the changes in the phenology.
I understand. Yeah, and also, did you calculate leaf area index separately from MODIS, as I know that MODIS already has, or?
That's right. So we had in developing the surface data set, of course, we focused on the state of vegetation because we had noticed that that's important. And what I did actually is kept the MODIS leaf area index the same per pixel, but partitioned that into vegetation types more accurately, using the phenology that we observed on the ground, the seasonality, to identify MODIS pixels as winter wheat as opposed to grass. I suppose you could consider grass to be a crop in the sense that it's cut and baled, but it's a very different seasonality than the winter wheat. And so the MODIS algorithm essentially just did not know about winter wheat and considered that to be a crop in the same category as the grass. So we think we got a better description of the surface, but still relying on the leaf area index retrievals that they produced. And when combined with the land model parameter set that we developed for that site, we found very dramatic changes in how surface heterogeneity was represented in the model. So that was part of that study that I cited.
I understand. Thank you so much. And what other questions do we have, the audience, to Dr. Williams?
So feel free to either enter in the chat, or if you're comfortable unmuting yourself and asking the question, either or is okay.
Hi, Dr. Horton.
Dr. Williams, hi.
Hi,
I enjoyed the presentation. Thank you so
thank
much.
you.
I was a little bit curious to ask about your use of soil moisture or soil water content. I think you said it was just the top 10 centimeters.
Yeah. Yeah.
And it seems to me, you know, that might be somewhat correlated, although even that's iffy, to soil water evaporation, but much less connected to transpiration rates.
Right.
Is there any use of deeper soil moisture, like the root zone soil moisture,
Yes.
correlated to transpiration, and
Yes.
really close to the surface soil moisture for soil water evaporation?
Yes. Thank you for asking that. I did look at that. So there are a number of sites that have the deeper soil moisture measurements down to 60 centimeters, sometimes 100. And somewhat surprisingly to me at the time, I did not see a dramatic improvement in the sorts of correlations or in the in the scatter plots showing the seasonal progression. It's yes, it does become a little more tightly related to that root zone soil moisture. Um, One thought was that maybe plants have some way of integrating over that whole volume, so we don't really know how to do that integral. And I started thinking about ways we could recover this soil moisture dependence more clearly. And in the end, I decided that, well, plants provide the solution for us because they give us gross primary productivity and so on. And so in the end, I used that. But I mean, absolutely, I don't want to give the wrong impression that I'm saying that it's all dictated by plants. It's really more that they're mediating this connection, this dependence to the soil moisture. Of course, we see in the drought periods that net ecosystem exchange of CO2 and ET really does drop dramatically once you pass some sort of threshold in soil moisture.
Thank you.
Any more questions?
May I
I had a
ask
quick
one more
question.
question? Did you have a question?
Yeah, so
Okay, you
my
go first.
understanding of law is very limited, so bear with me. But so you talked about the parameterizations and how you're setting these, and these can kind of create biases, right? And I believe I also asked this last week, but for any of these, how are they like calibrated, or how do you determine that bias? Maybe I just missed it, but could you clarify that a bit?
Yeah, that's also a good question, and it's a difficult one to answer. So in the slides I showed, we're comparing historical simulations to observations, accounting for differences in the model scale to the extent that's necessary. It would be a whole seminar to talk about how you do that comparison of field scale measurements to a climate model, but it can be done. So yeah, we run the models for historical periods of time. Sometimes they are running freely, so allowing the climate to respond to the model's own coupled ocean and land surface. And in other cases, we run them initialized with some observed data set, and then we look at how the simulation drifts from observation, starting with that forcing the model to be in the state that we observe at some time. And I showed some examples of that sort of a comparison in the talk. So that's the use of hindcasting is what we call it. So trying to forecast a day that weather event that occurred in the past, where it's a little clearer to see the impact of the model biases because you've eliminated some of the uncertainty in the part of the discrepancy that would come from the initial condition being off or from the boundary conditions being off from what is observed on a specific day. If you allow the model to run freely for some time beyond the initial condition or allow the boundary conditions to change interactively, then you have to do a more statistical evaluation. You can't just compare a day between observations in the model. You would have to look at some average over the model climatology compared to the observed. Does that help?
Yeah.
Dr. Williams, I also got a question. So does your model utilize regression? If so, can it be linear or nonlinear regression to make predictions? And how does it affect the results?
Yeah, so the numerical modeling is based on a time stepping procedure. So it's discretizing the physical space into time and space, discrete intervals, and then integrating in time physical laws, governing momentum and energy conservation. So we don't rely directly on those kinds of statistical models, but they do come into certain parameterizations where you might have some empirical relationship between the grid cell properties and the sub-grid scale phenomena. And off the top of my head, I don't know of an example of where linear regression is used, but nonlinear regression could be used. There's probably an example somewhere.
Thank you so much. Any other questions to Dr. Williams?
We are reaching our 2 p.m. time, so to be respectful of every times, I'd like to thank everyone for joining us today and to remind that next week we have Dr. Dina Howe from the ABA department and going to be presenting the Iowan microbiomes, native or captive. So please join us at the same time, same link. Thank you so much.
Thank you. Thank you, Dr. Williams, and thank you, everybody.